Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. Up to this point, you've probably watched a few of my videos on optimization problems in calculus. And we've optimized things like distances and areas and volumes. And now we're into optimizing time. And usually when that's involved, you're talking about minimizing time or minimizing time specifically, because time is worth money. You want to minimize that. Not money, but you want to minimize your time doing something, right? So this is a very classic problem presented in a lot of different ways, but I like this wording of this problem. It's just kind of fun. It's tongue-in-cheek, one of my favorite problems. So let's read it, and it's the only minimizing time problem that I have here. So single question video. If a dog swims at 1.2 yards per second and runs along the shoreline at 3.0 yards per second, and we know that a ball that has been thrown is 50 yards up the shore and out to sea 15 yards, where is the best spot for the dog to enter the water so that he minimizes his fetch time, basically? So I've read the problem. It might be the case that you're looking at that going, I don't know what is going on with this. So let's draw a picture. We have a shoreline. I will use this for our shoreline here. There we go. There's our shoreline. Right? And let's just pretend that we are standing right here. That's the start. That's where we're standing. And we throw a ball, according to this problem, 50 yards up shore and then 15 yards out into the sea or the ocean, whichever you prefer. So it'll go up 50 yards and out 15 yards. Let me go ahead and just pretend that that's like right here. So that point is out 15 yards. Let me zoom in and kind of label that this distance right here is 15 yards out into the water, 15 yards. And the distance up, this distance right here, is a total of 50 yards. Okay, and we have a dog, and the dog wants to get that ball. It's just like, let me get the ball, let me get the ball, let me get the ball. Okay, great. And so we let the dog loose, and the dog starts running up the shoreline really quickly. I'm gonna run. And at some point, if you've ever played fetch with a dog, they know when to turn a corner to jump into the slower paced area, so into the water. So we want to find what is the optimal place for a dog to jump into the water so that they can get to that ball as quickly as possible. They want to minimize their time getting to that ball. Remember, they are pretty decently fast along the shoreline. They move along the shoreline or this sandy beach at 3.0 yards per second. They swim at 1.2 yards per second. 1.2 yards per second. That's their rate of movement in the water. So I hope all of that makes sense. We want to minimize time. So let me just state that off to the left here. Minimize time. Or minimize fetch time if you want to say that. Okay, so we need to develop a formula for time. And we've been given distances and speeds. This is like the most popular formula in algebra. D equals RT, except we want to write it in terms of T. So we're going to use T equals D over R. And I'll just say let T, the total time spent getting this ball, be the time along the shoreline plus the time in the water. That should make sense. There's some time running along the shoreline, and there's some time spent in the water. Each of those formulas, time spent on the shoreline and time spent in the water, can be written in terms of D over R. So the distance along the shoreline over the rate along the shoreline plus the distance in the water divided by the rate in the water. And the distance along the shoreline, well, let's call that, we have two choices here. We could call this distance x or this distance x. From my experience, I'm just going to tell you, it's easier to call this distance, it's easier to call this distance x so that this remaining distance is 50 minus x. The reason why I say it's easier to call this distance up here x is because you're going to use the Pythagorean theorem to find out what the hypotenuse distance is. And that's just much easier if you only have a single term in that expression rather than an x minus 50. Yeah, I think it's a little bit better. So let's see. The distance along the shoreline is 50 minus x. 50 minus x. And the speed along the shoreline is 30 yards per second. But 30, I'll just say. Or 3.0. I'm sorry, it's not 30, it's 3.0. I just didn't see the period there, but it's 3.0. Plus, the distance in the water. Well, the distance in the water here is the Pythagorean theorem. That's going to be the square root of x squared plus 15 squared. So that's what I'm going to write here. Distance in the water is the square root of x squared plus 15 squared, which actually is 225. And the rate in the water, how quickly the dog swims, is 1.2. Again, yards per second. That is our time formula. Notice it only involves two unknowns, t and x. So this is ready. We can actually do this. There's no kind of restrictions for us to just start taking the derivative. And I probably would not bother combining terms here. That would be just a mess. So t prime, to find the critical numbers, is going to be, if you can imagine, this first fraction, which is 50 minus x over 3, can be written as 50 thirds minus x over 3. And that way, the derivative of the first part is 0. Derivative of the second part is a negative 1/3. It's just a little bit easier to deal with that. Plus, the derivative of this chunk right here, well, it's going to be 1 over 2. Well, let me write the 1.2 at least. 1.2, and then times 2 root x squared plus 225. And then times the derivative of that x squared plus 225, which is just 2x. That actually is not too terrible, other than the fact that it's got decimals and stuff like that. This t prime is always defined because you don't have division by 0. So we don't have an issue there, but t prime is equal to 0 when, first of all, 2's will cancel beautifully, so I can at least do that. When this stuff right here is equal to 1/3. So when x over 1.2 times the square root of x squared plus 225 is equal to 1/3. Cross multiply, if you like to say that, and that would become 3x is equal to 1.2 root x squared plus 225. Square both sides, you get 9x squared is equal to 1.44 times the quantity x squared plus 225. And then start moving things around, right? So if you start moving things around, let's see, I'm going to grab a calculator because I need 9 minus 1.44 and I'm too lazy to actually think right now. So that would give me, if I subtract 1.44 x squared from both sides, I would get 7.56. X squared is equal to 1.44 times 225, which is 324. Divide both sides by 7.56 and take the square root. And you will get x is approximately equal to, so the square root of 324 divided by 7.56. Just make sure that I typed everything in. Yes, I did, roughly 6.5. Now, I want to create that number line. I'll plot 6.5 on it. Let's talk about realistic values for x. Realistic. Your dog could be really, really, really dumb, I suppose, and run all the way past this. But let's assume your dog is not that stupid. And instead, let's just pretend the minimum X could be a 0. In other words, the dog could run all along the shoreline and then hop in the water. Okay. So the minimum value for X will be 0. The maximum value for X, as long as your dog's not stupid and runs this way first, the maximum value for X would be 50. So that's just where the ball started. So now you could test values. So go to T prime, which is this value up here. And you're going to plug in values between 0 and 50. And actually, you could plug in 0 and you can plug in 50 if you want to. If you plug in 0, you will get negative into, if you plug 0 into T prime, sorry, you'll get a negative. So T prime of 0 is less than 0. So we have negative. So time is decreasing. And then you could plug in 50. Well, 50 is not really going to super help out, but if you plugged in 50, you'd get 50 over 2,000 something on minus 1/3. I'm just going to tell you right now it's positive. Too lazy. T prime of 50 is greater than 0, so it's positive. So your time function is increasing. So basically the time it takes is decreasing until you get to this X value right there. And at that point, it starts to increase. And so this is the minimum amount of time that it would take, or I'm not minimum time. That's the minimum. That's the best point to enter into the water so that the dog minimizes time. That's the best way to say that. So how are we going to say that in the answer? Where's the best spot? So the dog should run. I'm going to pause. The dog should run upshore for not 6.5. By the way, that says min, but minimum is what I meant to say there. The dog should run upshore not for 6.5 yards, but actually for 50 minus, because X is 6.5. So for 50 minus 6.5 yards. And actually, that's an approximated 6.5. So I'm just going to do the 50 minus. That's 40. Well, that is 43.5 though. So the dog should run for 43.5 yards and then get in the water. And that's because we found out that the time function is minimized when X, which is the distance here, is 6.5. That is, the dog ran along the green path for 50 minus 6.5 or 43.5 yards and then hops in the water. There you go. That is a good minimized time problem. You'll see these also written as minimizing costs. So somebody's laying pipe into ground and it's really cheap to dig into the ground, but they have to get across the river at some point and it's really expensive to dig across the river. So where's the best point to start digging into the river? That's a fairly typical, again, example like this, but in that case, it's minimizing cost.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much. That isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.